Okay, good morning, everyone. Any questions before we wrap up this section, this chapter, basically? All right, so we will do one application to Taylor series, so section 11.4, I think. So a little bit 36, 42. 36. 36, I did it yesterday, Chris.
Oh, okay. Can you just do 42 then?
Yeah, 42. I'm gonna do it once I do the application. All right, but 36, if you remember, I did it yesterday.
All right.
Yeah. So, and 42 is basically the same idea. So it's not everything we do is the same idea. So 42, sorry, application to Taylor. Now the main reason, as I said, we use those series is actually to approximate function by linear, by the tangent line, by the quadratic, by the cubic. That's really the main reason we use them. And that's how you guys will use them in physics, mainly in physics. That's how you use them. So application to Taylor series. Okay, the application we're going to see is along the following line. We learned how to integrate, how to find the antiderivative. But a lot of functions, we actually are very hard to find not only hard, it's actually impossible to find their antiderivative as a function, as a combination of sine and cosine of e to the x. So for example, if I take something like that, sine x squared. Be careful, there is x squared here. There is no x outside. There is nothing. It's just the sine of x squared. Regardless what we try to do, nothing we've learned will get us anywhere. Not because we didn't learn enough, we did, but no integration techniques will help me to find the antiderivative as an easy function, as a sine or a cosine, or basically it has to be sine and cosine because that's a sine of x squared. So, or a combination of x and sine x. Nothing really actually would work. The only way we can find the antiderivative is as a series. So the only answer to that is going to be actually a series. So where is the series coming from and what's really going on? So here is the idea. Suppose you have a function f of x. Okay, so a theorem. Okay. Suppose you have a function f. And I wrote this function as a power series, either by manipulating another series or by using the formula itself. So suppose f of x could be written as a series, c0 plus c1x. I'm going to put it a series in x to make it a bit simpler, but instead of x, we can have x minus a, but I will do it the simple case, plus c3x cubed, plus so on. So suppose a series could be written like this. And if you want, we can go all the way to its sigma notation. And let us suppose that this holds when the absolute x less than certain number r. Okay, because we know that the conversions occur not for all x, for absolute x less than r. All right. Then the idea that we can integrate the power series. And the way we integrate it, so we can find the antiderivative of f of x dx. Okay, and we do so. The integral of f of x dx is obtained by doing term-by-term integration of the original series. By doing term-by-term integration. So what do I mean by that? This is a function. When you find its antiderivative, is a whole new function, a totally new function. Okay, so antiderivative of x is a new function, which is half x squared. This tells me that the antiderivative is equal to, so the series that will represent the antiderivative is obtained by integrating each one term by term. It means it's equal to c0 dx each term dx plus x squared dx plus c3 x cubed dx plus etc., etc., etc. It means that the antiderivative of f of x, this term by term integration is really what I want you to memorize, that we can integrate a series term by term. It's going to be equal to C0x, because that's the antiderivative. C1x, C1 is a constant. Antiderivative of x is a half x squared plus C2 is a constant. Antiderivative of x, it's C2 x cubed, and so on and so forth. C3 x3 over 4, C4 x4 over 5 plus so on. So if I know the power series of a function, I know immediately the power series of it is antiderivative. It's given by taking the original one and integrating term by term by term. And this new function will converge for the same interval that the original one converges. And also we can do definite integral. Moreover, if I take the definite integral from a to b, the definite one, f of x dx, is going to be equal to, since I know what the antiderivative is, so we're going to take the antiderivative, which is a series evaluated between a and b. So basically the whole idea, if you have a function is written as a power series, its antiderivative is obtained by doing term by term integration, and so on and so forth. Okay. All right, so we're going to use this idea to find first the power series of tangent inverse, because that's really what problem 42 is about. And once we establish it, we will do 42 exactly. Okay. So idea is simple. If we think of series as polynomial, if you want, of infinite degrees, which is actually what series are, generalization of polynomial, then integrating the function like integrating this polynomial, which is obtained by integrating every term, term by term by term. Right. So find example 1. Okay. Find the power series or the Maclaurin series. Power series in X, or, because they mean the same thing, Maclaurin series of f of x equal arctangent x. So how I'm going to find the power series of arctangent? I don't want to go through the formula. You can try to go through the formula yourself, and you will realize it's a nightmare very soon. Okay, it's very hard because it's going to involve f of x, f prime. F prime is 1 over 1 plus x squared. Then you have to deal derivative of 1 over 1 plus x squared, which is going to be like 2x, 1 plus x squared to the power minus 2. Then you start hitting the product rule, things become nightmarish. So the question is how we're going to find the power series. We're going to relate it to something we know. All right. Anybody related to something we know? Let's recall that arctangent x is the antiderivative of that. Okay, because the derivative of arctangent, so let us remember that the derivative of arctangent is 1 over 1 plus x squared. So arctangent is the antiderivative of 1 over 1 plus x squared. And now this is what we do. We know the power series of 1 over 1 plus x squared. To get the power series of arctangent, we just integrate term by term, we get the arctangent. So let us do it. So we're going to start with the following. 1 over 1 plus x, because I want 1 over 1 plus x squared, so I start with 1 over 1 plus x. Now this is basically the geometric series. This is given by that. I will not write everything in details this time because we don't need it.
What does that say? Arctan, the derivative of it says.
Yeah.
What does it say? Can you move the paper over a little bit?
Oh,
Okay, thank you.
oh, sorry. Thanks, Grace.
You're welcome.
All right, so this is 1 over 1 plus x. Now I want 1 over 1 plus x squared. And this hold when x is between -1 and 1. And dot, it means there is a pattern, plus x6, minus x5, and so on. Now 1 over 1 plus x squared is equal to, I'm going to substitute x squared for x here. 1 minus x squared plus x squared squared, x squared to the power 3, x squared to the power 4, x squared to the power 5, and so on and so forth. Okay. So it means this is equal to 1 minus x squared plus x4 minus x6, x8, x10, etc. So if I want to write it in sigma notation, which is not really hard, it's -1 to the n, x to the 2n. That's really in sigma notation. And this works for x between -1 and 1. Now I need antiderivative. I need arctangent. What's arctangent x? It's the antiderivative of 1 over 1 plus x squared dx. And now that's the idea. If I know the power series of 1 over 1 plus x squared, the power series of its antiderivative is the term by term integration. Means basically I'm going to integrate every term by itself. Every term is going to be integrated. So let's do that. Antiderivative of 1 is x. That's really what it means. Now, x squared. Antiderivative of x squared is 1 over 3 x cubed. And this will give me the antiderivative or the power series of arctangent. Plus, antiderivative of x4 is 1 over 5 x5. So term by term, minus 1 over 7 x7 plus. So I'm integrating that. Sorry, my mind went totally blank. X minus this, x4, I'm right, x7, I'm fine so far, x8, so it's going to be 1 over 9, x9, and so on and so forth. So in sigma notation, this is going to become the following. What I am doing, I'm integrating each term. So this will become -1 to the n. Antiderivative of x to the 2n is 1 over 2n plus 1 x to the 2n plus 1. Because antiderivative of x to the 2n, you just take 1 over. So you add a power, 1 over the power plus 1, x to the power 2n plus 1. And this will give me the power series of arctangent. Okay, and this between x between -1 and 1. Okay, so using what we know to find the arctangent, power series of arctangent is become much simpler. And as I said several times, once we know this, the way we work with those, the way people work with this is that when I have the arctangent, especially near 0, they start approximating it. So they approximate by x. If they want a better approximation, they do x minus 1/3 x cubed. That's really how people use those ideas. Even better approximation, they can go to x5. But we don't use a very high polynomial because it defies the purpose of the approximation. Usually people use actually the first 2 terms or the first 3 terms at most to approximate the arctangent.
I have a question.
Yes, please.
How did you start? Because I know you did arctan x equals the antiderivative of 1 over 1 plus x. That's how you started this problem, correct?
It's the antiderivative of 1 over 1 plus x squared, right? What?
I'm
Great.
just wondering how like you did that.
I try to relate this to something we know. That's the idea. So we know that the arctangent is the antiderivative of 1 over 1 plus x squared. So what I did is I tried to find the power series of 1 over 1 plus x squared and then integrate it. And the question is how to find the power series of 1 over 1 plus x squared. To do that, we should start with 1 over 1 plus x. Because we know this, I can find 1 over 1 plus x squared. If I know how this could be written as a series, I integrate it term by term, I get the arctangent. I don't know if I'm answering your question.
Yeah, okay, that makes sense. So you just have to find the antiderivative
Right,
of
because
first.
I know it, because we know that we know the power series of this one. So because we build it up, so we know what's its antiderivative, and this will give me the arctangent. So it's making connection between things. I mean, it's what we're doing is relating what we want to find to something we know. So we have those basic ones, e to the x, sine x, cosine x, ln of 1 plus x, that we have to work them out clearly. And then arctangent, to find it, this one of the function which is used, we say, okay, we can use the formula, but it's nightmare. We cannot get through it. We relate it to something we know. Okay, it's the antiderivative of 1 over 1 plus x squared, but I know this one, so I can find the arctangent. So we relate it to something we know. And the theorem I've mentioned, that we can integrate the power series, will help us to be able to do that. Okay. Now that we have the power series of arctangent x, we can start using it. We don't have to derive it every time. This is one of the series that you don't have to derive. This is one of the series that you can use. Based on this, I'm going to look at number 42. So number 42 is the following. So we have the following function. F of x equal x times, if my memory is right, x times tangent inverse or arctangent x squared. Okay. All right. And the question is, find the first non-zero term of the Taylor series for non-zero term. So they don't want everything. They want only the first 4 non-zero term. At least that's the question in the book. And then write the power series. All right. So basically, they want us to write the power series of this function. Now, as I said, Maclaurin using the formula, it's a nightmare in this scenario. So how are we going to do it? I know the tangent inverse. I'm going to find, so we're going to start with the tangent inverse that we just did. Then I'm going to do the tangent inverse of x squared, and then I'm going to multiply by x. That's how we're going to do it. So let us get started. It may take a little bit of time, but it's not really too bad. So the tangent inverse of x. The tangent inverse of x could be written. So I'm going to start tangent inverse of x. And it's equal to, according to what I did a minute ago, x minus 1 over 3 x cubed plus 1 over 5 x5 minus 1 over 7 x7 plus etc. And in sigma notation, it's sigma minus 1 to the n x to the 2n plus 1 over 2n plus 1. And it holds when x between minus 1 and 1, n equals 0 to infinity. Okay. Now, what I want is the tangent inverse of x squared and multiplied by x. Now, tangent inverse of x squared is easy. I'm doing it step by step. So we're going to substitute x squared for x. So I will have tangent inverse x squared equal x squared minus 1 over 3 every place there is x, I substitute by x squared, plus 1 over 5, x squared to the power 5, minus 1 over 7, x squared to the power 7. I kept the first 4 terms because they want the first 4 terms, plus etc. So in sigma notation, I'll write the sigma notation here. Sigma of minus 1 to the n, x squared to the power 2n plus 1 over 2n plus 1. And this holds here. My n goes from 0 to infinity. Okay. Now, if they want x times tangent, I'm going to add something. They want x times tangent. It means I have to multiply everything across by x. That's really what they want. So I have tangent inverse. If they want x times tangent inverse, I take tangent inverse of x squared and I multiply it by x. And this is the function they are after. Now the rest is basically to simplify the whole thing. So it's going to be equal to. So f of x should be equal to x times x squared. Now I'm getting rid of those parentheses. x6, x10, x14, plus so on. So it's going to be equal to x times sigma minus 1 to the n. As we decided yesterday, we multiply the power. So this will be x to n plus 2 over to n plus 1. N equals 0 to infinity. Okay, the last step is the following. We just distribute the x. It means you multiply term by term. We just basically distribute. So I will have f of x equals. So the last step, which is going to give me the series the way we want. X cubed minus x times x6, x7 plus x11 minus x15, etc. Now in sigma notation, because I want it in sigma notation, it becomes sigma minus 1 to the n over 2n plus 1 x to which power? I stop. This is easy because I'm just multiplying. What do you think gonna be the power here?
2n plus 3.
Absolutely. Because you're taking x, each x you're multiplying to n plus 3. Because you're multiplying by x every time. You're adding to n plus 3. End of the problem. And this whole for x between minus 1 and 1. So once we know the tangent inverse, that's we derived it a minute ago, and then you want x tangent inverse of x squared, you just use what you know to figure out what you don't know. Now, let us say I told you find the first 4 terms, let us say, which is something I usually do. Find the first 4 terms of the Taylor series or the Maclaurin series. In this case, you don't have to do the whole thing. You basically stop at the first 4 terms. So it means in this case, I'm not asking you to sigma notation. I'm not asking you anything. I'm just interested in the first 4 terms. Means I'm going to use those to approximate the function. Find the first 4 terms. You have to stop right there. That's the first 4 terms. Find the first 3 terms. You just give me the first 3 terms. If I don't ask about the whole sum, about terms, then you stop when you hit the first 4 terms. End of the problem.
I have a question real quick.
Yeah, yes, please.
Would the x wouldn't be the 3n plus 3 instead of 2n plus 3?
Oh,
the sigma?
No. Watch carefully. Watch carefully. What are we doing here? I'm going to add one line. Okay, one piece. Thanks for asking. Okay. What I'm doing is I'm distributing the x for every term, like I did here. So if I think of this as the general term, I am multiplying it by x. The student to ask the question. You understand what I did?
Yeah, but I'm saying like at the bottom, wouldn't it be like 3n plus 3? Because
No. Listen to what I'm saying. How do I get this term? How am I doing now? I am basically distributing the x. Watch here, and not the sum. Watch this piece right there. Okay, when I distribute the x, what do I do? X times x squared, what will happen to it when I distribute the x?
you add the exponent, so x cubed.
No, yeah, here, what do I do?
Add the exponent, so it becomes x7.
Right, what do I do?
Add the exponent, it comes x11.
What do I do? I'm on purpose doing this.
Add the exponent, x15 becomes.
Right. If I think of the general term here, okay, the general term is going to be this one. So that's the pattern. Plus, etc. You understand what I mean by that term?
Yeah.
Okay. If I keep distributing, what I'm going to do? X cubed, x7, x11, x15. When I hit this term and I multiply by x, what am I doing?
Okay, you're adding one.
Right.
Okay, that makes sense. Okay.
Yes, it's x to the 2n plus 1. You're multiplying it by x. X raised to the power 1. So what do we do? 1 plus 1. Sorry. Did I do something wrong? That should be 2n plus 2, my apology. Yeah. Okay, 2n plus 2, because I didn't copy. Okay, so this is going to give me 2n plus 2 plus 1. 2n plus 3. Is it making better sense?
Yeah, I got it. But okay, so the sigma, does it equal the f of x? So if we check it, then it should equal the...
Here and here?
Yeah.
Oh, yeah, it should. Otherwise, I did a mistake. If n equal to 0, minus 1 to the 0, which is 1, n equal to 0, x cubed.
Yeah.
Correct? N equal 1, minus 2 times 1, that's it, 2 plus 1 is 3. If n equal to 1, I will have 2 plus 3, which is 5. So I must have skipped.
That's why I was confused.
I know. What's my mistake? I want you to tell me. I'm not going to tell you. I found my mistake. You guys should have screamed. What's my mistake? I have a mistake. You guys should find it. +1 on the quiz tomorrow if you find my mistake. Here you are.
Should have been x squared to the 2n plus 1 initially. So it.
What was the mistake? I did a stupid mistake. I want you to find it.
You have to multiply the 2n by 2.
So where were my mistakes?
4n plus 2, shouldn't it?
What this should be?
4n plus 2.
Right. That's my mistake. That's my mistake. You guys should have corrected me. Because when I took x squared to the power 2n plus 1, so that's my mistake. I like mistakes because it helped me to explain things better.
Because I was confused because I was trying to plug in the first
right. Absolutely right. But what I was explaining here is my explanation.
Yeah, okay. I get that
this is
part.
why I'm adding 1, but I didn't pay attention to this piece at all, actually, honestly.
Yeah.
This is x to the power, you multiply 2 times 2, that's it for n.
Plus 2, okay.
Plus 2, thank you very much. So this is gonna go for n plus 2. Everything stays, but this is gonna become for n plus 3. So the plus 3 is the correct part. I messed up at this stage. And now you're right. Now we're going to go through it again. At 0, I am fine. If n equal to 1, That's minus over 3. 4 plus 3, it's 7. I'm fine. N equal to 2 is a positive. 2 times 2 is a 4 plus 1, it's a 5. 4 times 2, it's 8. 8 plus 3, it's 11. I am fine. All right, so now you're absolutely correct. And then I keep going. If n equal to 4, n equal to 3, I will have minus 2 times 3, 6 plus 1 is a 7. 4 times 3, that's a 12. 12 plus 3, it's 15. I am on the right track. All right, so the mistake was basically I didn't multiply correctly. It should be for n plus 2. Otherwise, everything is correct because that's what I'm doing. I'm distributing my x, giving me the 4n plus 3. I'm adding a power. Thanks a lot for your questions. Any other problem? Right, so the last thing I'm going to do, and that's it for this section. That's it. I'm done with this chapter. We're going to move on to easier material, way easier, is the following example. One of the functions, as I said before, some functions are hard to find their antiderivative. So one of the functions that almost is impossible to find its antiderivative as an easy function is the exponential minus x squared. So my question is, let us consider the following integral. Integral from 0 to a half, if you want, of e to the minus x squared dx. Okay, now, if I'm giving you this integral usually, and I tell you to evaluate, you have to find the antiderivative. E to the minus x squared is again one of those functions, regardless what we try. We cannot find antiderivative as an easy function. So the way we're going to do it, we're going to express this integral as a series. So my question number 1 is the following. Write the integral. Now remember, the integral is a number because that's a definite integral. So we're going to write it not as a power series, of course. I'm going to write as a series because it is a number. So how we do that? How we write this as a series? Okay, the way we do it is we first find the power series of e to the minus x squared, and then we integrate term by term. So I will do it here. I want the power series of e to the minus x squared. I start with ex. Okay, so you guys, if you're writing, say we need to find the power series of e to the minus x squared. So start by finding power series of e to the minus x squared. Okay, and then I want to integrate it. Now, e to the minus x squared, if I want to find its power series, definitely I don't use the formula for the Maclaurin. We start with what we know. So we start with ex. Okay, so I want to integrate e minus x squared by finding the power series of e to the minus x squared. And then I integrate it. Okay, to do that, you start first with ex. Ex is this famous one. 1 plus x plus 1 over 2 factorial x squared. 1 over 3 factorial x cubed. 1 over 4 factorial x4. 1 over 5 factorial x5 plus etc. Okay. And this works for all x. Now, e to the minus x squared, we're going to substitute minus x squared for x. And I will get e to the minus x squared equal 1 plus minus x squared. So wherever there is x, I put minus x squared. Plus 1 over 2 factorial. Wherever there is x, I'm going to put minus x squared. I'm going to try not to do a stupid mistake this time. Minus x squared. So I'm going to only find the first 5 terms. To the power 4 plus that, etc. Okay. Now we're going to write e to the minus x squared equal to 1 minus x squared plus 1 over 2 factorial x4. Now I'm getting rid of this mess. x6 plus 1 over factorial x8 plus, there is 1 plus plus minus 1 over 5 factorial x5 plus so on. Okay, so that's e to the minus x squared. Now the antiderivative.
That last one be x to the 10th.
Of course, I'm doing mistakes. X to the 10. Very good. Now I need the antiderivative of e to the minus x squared dx. At this stage, I have a definite integral. It's going to be the antiderivative evaluated between 0 and 0.5. So at this stage, what I'm going to do is term by term integration. So term by term integration. It's going to be x minus. This time, probably I will not finish the whole thing because usually a pattern emerges. And so antiderivative of 1 is x. So that's the antiderivative. Antiderivative of this is x cubed. Antiderivative of that is 1 over 2 factorial, x5 over 5. And then antiderivative of this term is minus 1 over 3 factorial times 7, x to the 7. And I will do one more term and I'm going to stop. I'm not going to keep doing. So this is going to give me x9 over 4 factorial times 9 plus dot dot dot. Okay, finally it's equal to. I'll take another piece of paper. And this will give me the integral from 0 to 0.5 e to the minus x squared dx. So what I'm doing is, first, this is the antiderivative of e to the minus x squared. So I'm finding the antiderivative. And then using the fundamental theorem of calculus to evaluate it. Okay, antiderivative and then the fundamental theorem. The antiderivative is obtained by integrating every term by term. And now the fundamental is the value at the upper minus the value at the lower. So the value at the upper is 0.5 or a half if you want, minus a third plus 1 over 2 factorial times 10, times 5, 0.5 to the power 5 minus 1 over 3 factorial times 7, 0.5 to the power 7, and I will write one more term. And this is 0.5 to the power. What am I doing? Okay, 9 over 9. Plus, etc. Minus the value at 0, which is 0. So finally, my last step here, we get integral from 0 to 0.5 of e to the minus x squared dx is given by this series.
So how do we know how many terms to integrate? Do they tell us, or do we just do like the first?
I will tell you. I will tell
Okay.
you. I will tell you. Okay. I mean, I'm going to add another question here, which is probably make it. That's a very good question. This is a hard question sometimes. So tomorrow I will tell you. Plus, etc. Okay, it keeps going. All right. Now my second question is the following. It's a bit harder, but it's not. Question number 2. Use enough term of the series so you can approximate. The integral, the definite integral, with an error less than 10 to the minus 4. Okay. So this is a little bit hard, but not very hard. Let's see what's really going on here. If I look at this power series, sorry, at this series, it's an alternating series. Am I right? Plus, minus, plus, minus, plus, minus. It's going to alternate. And we know something about alternating series, which is the following. If I use the first two terms to estimate the sum, the alternating series tells me that the error is less than the term that the first term we neglect. If I use the first three terms, the error is going to be less than that. If I use 1, 2, 3, the first four terms, the error is going to be less than that. So the question is, use enough so you can approximate with an error less than 10 to the minus 4. So how are we going to do it? The book does it in a very formal way, but I'm going to do it in a more intuitive way like that. So I want to say something. All right. So the idea is the following. Suppose I use, so we're going to do what we call trial and error. Trial and error. And usually it's not too bad. Suppose I use the first three terms to estimate. So by the alternating series test, suppose I estimate the integral with the first three terms, with S3. The error is going to be less than what? 1 over 3 factorial times 7 times 0.5 to the power 7. So F3, I mean the first few terms. So F3 here is 0.5 minus 1 over 3, 0.5 to the power 3 plus 1 over 2 factorial times 5, 0.4 to the power 5. This is what I mean by F3. So this is going to be the error. And now I ask myself, is this less than question mark 10 to the minus 4? That's what I mean trial and error. If it is, I use those to estimate. If not, I add an extra term and ask myself, will the error be less than 10 to the minus 4? So at this stage, we just honestly pick up our calculator and see, okay, is this working? I mean, is this number less than 10 to the minus 4? So I actually don't know. I'm going to compute it. So this is going to give me is 0.5 to the power 7 divided by 3 factorial, which is 6 times 7 times divided by 42, which give me 1.86 e to the minus 4. So this will give me, so this term here is 1.86 times 10 to the minus 4. Means if I use the first three terms, that's the maximum error. Is this less than 10 to the minus 4?
Yes.
Is it?
No.
No, because it's 1.86 times 10 to the minus 4. So it's not less than. So this is no. That's what I mean by trial error. So what do I do in this case? I add S4 and ask myself, would my new error bill be less than 10 to the minus 4? So trial and error, so this is fail. And usually you're not going to need a lot of terms, otherwise it becomes absurd. So finally, now I'm going to try minus, I'm going to take this integral, minus S4, means the sum of the first four terms. Now I go to here, 1, 2, 3, 4. If I use those, the error is less than this term right there. So this is going to be less than 1 over 4 factorial times 9, 0.5 to the power 9. And now I'm going to compute this number and ask myself, is this less than 10 to the minus 4? If it is, it means I am safe and I'm stopping right there. So let's compute that. It's 0.5 to the power 9 divided by 4 factorial, it's 24 times 9. Okay, I'm getting almost 9.04 times 10 to the minus 6. It means this is definitely less than 10 to the minus 4. So, which means that I can use the sum of the first 4 terms to estimate the integral with a very, very, very tiny error. So S4, so the integral, we're going to estimate it with S4. But what is S4 is the sum of the first 4 terms. So that's some application to how we can use those ideas. 0.5 to the power 5, but then I have to add one more term, 1 over 3 factorial times 7, 0.5 to the power 7. So those are enough to approximate the actual value with an error less than 10 to the minus 4. Now I can add those. I added them yesterday, but I somehow threw the paper away. Yeah, for some reason I threw the paper away. So if we find the sum, we pick up our calculator and we add them, we physically add them. And we use our calculator to find the exact value of the integral, which is done by a Riemann sum type procedure. We get almost the same value with a mistake after the 4th decimal place. So we get a very good approximation.
I have a question.
Yes.
So we always add the next value because
Yes, you keep taking sums till you hit a place where your error is less than 10 to the minus 4. Okay, so you use the first 2 terms. That's what I mean by trial and error. And since this is alternating, and we can only do that for alternating, if you use the first 2 terms, the error is going to be less than that. You ask yourself, is this less than 10 to the minus 4? If it is, you're safe. If it's not, you use
I go on to the next one.
What? Yes, you move on. You ask yourself, is this less than 10 to the minus 4? If it is, it means the first 3 terms will estimate it with a small error. Not, you're going to move. Chris?
Pardon me? I'm sorry, I couldn't hear you back down for a second.
Did you understand what I'm saying?
Yes.
All right, so Hazim is giving me, which one is this Hazim, the actual value or the estimate?
The estimate.
So this is the estimate. 0.46127, that's the estimate. The actual value is the one you pick up from your calculator. Does anyone of you know how to use the calculator to find the antiderivative, or use the whatever program you guys use? What kind of the actual value should be 0.4612, and the change should happen at the 4th decimal place.
It's 0.46128.
612 4 decimal places. They should be the same.
Yep.
They change after that. Absolutely, because we're finding the error within 10 to the minus 4. So we have a very good estimate of the actual value of the integral.
I have a question.
I'm listening. And I'll get to you. Historically, people had no calculators. Historically, people had to do all those kind of math because there were no calculators. So they needed to estimate ideas. And that's where a lot of those math is being developed, and now we use it. They had to estimate. They couldn't, there's no way they can find the antiderivative. They actually estimated by using those series. They had no way out. Okay, go ahead, your question.
In the equation, right in the middle of the paper there, the e to the negative x squared minus s to the 4th. How do you figure that that's equal to that right there, the 4th?
It's less than, because in the alternating, if you remember a little bit when we studied alternating series.
Yeah, I remember like we talked about it, and I remember just not understanding it completely.
Yes, when the series alternate, so that was the idea. When a series alternate, okay, so the series goes like this. A1 minus A2 plus A3. It has to be alternating, otherwise what we're doing doesn't work. Okay, that's my series. And if you use the first two terms to estimate this actual value, you don't get the actual value because there are a lot of terms which are left. The alternating tells me that if you use the first two terms, the approximation, there is an error, and the error is less than the terms that comes after that, A3. If I use the first three terms to estimate the sum, the error is less than the terms that the first neglected term after S3, which is A4. And that's what I'm using.
Yeah. Okay, that makes sense.
All right, so for example, if I take any series, suppose I take the series sigma minus 1 to the n over n squared, which is totally alternating. So minus 1, if n equal to 2, 2 squared, minus 1 over 3 squared, plus 1 over 4 squared, and so on and so forth. Minus, plus, minus, plus, minus, plus. Okay, so we don't know what the value of this actually is. I mean, but however, if I use the first two terms to estimate it, so whatever this is, and I estimate it by that, so this is S2, of course, I'm leaving off a lot of terms that I'm not taking. I get an error in the estimate, and the error would be less than 1 over 9, which is not already too bad. So the first two terms estimate the value of this whole sum with an error less than 1 over 9. It means basically, intuitively, it means this whole piece right here is less than 1 over 9. The remainder is less than 1 over 9. And if I use the first three terms, so the whole sum minus 1 plus 1 over 2 squared minus 1 over 3 squared, if I use those, that means the error become less than 1 over 16. So we have a better estimate.
Okay. Yeah, that makes sense to me. Thank
Better?
you.
Yeah.
Yeah.
All right, any other questions? Okay, so now you can finish your homework, and tomorrow we're moving, as I said, to the last part of the book, which is we're going to talk a little bit about what we call parametric equation, which are not hard. And we're going to talk about polar coordinate, polar curve, which is also not very hard. And we finalize with the conic section, ellipses, circles, and hyperbola. So the rest is not hard. We're done with the hard part. Okay, so class is dismissed. Anybody has any questions?